Hi, welcome to Calculus. Today we are looking at section 2.1, rates of change and tangents to curves. So in calculus, we're going to spend a lot of time on these sorts of ideas, and so we'll really flesh them out and make them a lot more specific in terms of what we mean as we go through the course, especially here in this first chapter. But for now, we're going to kind of start basic, and we'll work our way into things. So let's take a look at a function. So I have a function here, f of x, which we could call y, and it's equal to 16x squared. And I have a graph of the function, just a real basic graph. And I labeled a few numbers here because we're going to start looking at what's called an average rate of change, and then we'll move into tangents here shortly. So the idea is this: if you have two x values, in this case I have 3 and 7, and we'll see that on the next board a little bit better. They have function values that are associated with them, or y values if you prefer, right? We can plug in 3 and figure out what we get. We can plug in 7 and figure out what we get. I didn't label it on the graph, but that's okay. We'll be all right. And so what an average rate of change is, and that's where we're going to start, and I'll give you a formula for it here on the next board. But what an average rate of change is it's really just the slope that connects those two lines. Or, sorry, not those two lines, those 2 points. It's really just the slope of the line that connects those 2 points. And so we know how to find slopes. We'll get a formula for this average rate of change. We'll talk a little bit more about it, and then we'll move into tangents, which is going to be slope at one point, and that'll be something interesting to think about. So let me get a new board, and we'll go from there. Okay, so here is our average rate of change formula, and really it comes in 2 forms, but they're exactly the same. They look a little different, but they are exactly the same. So delta y over delta x, change in y over change in x. If you've never seen this triangle notation before, it's called delta notation, and in basically any science class that you take, and certainly a lot of math classes, it just means the change in something. So in this case, the change in y divided by the change in x. And so since y is equal to function values, we have f of x2 minus f of x1 all over x2 minus x1. You might remember that a little more commonly as y2 minus y1 over x2 minus x1 is just the slope of that line between the 2 points. Now we do have another form of this formula. F of x1 plus h minus f of x1 all over h, where h is not allowed to be 0 because you can't divide by 0. All this is h is just the distance between 2 x values, and we're going to keep it generic, and we'll see why here shortly. We keep it generic because what's going to happen is we're going to squish those 2 points together. And like I said, we'll see that here in just a few minutes. But you'll notice that this is the same function. So let's take a look at the example that I had before. F of x is equal to 16x squared. So, and I'll talk about why it works with either one of these. So I want to find the average rate of change on the interval from 3 to 7. Now, importantly, 3 is x1, 7 here is x2. All right, so 7 and 3. So the first thing I did was I found f of 3 and f of 7. I need those values. And once I had those, okay, and you can check my math, but I'm pretty sure that they're right. Once I had those function values just by plugging in 3 and 7, then I plugged them into the formula. F of 7 minus f of 3 all over 7 minus 3. And if you do that, you get 160 as our answer. Now, importantly, you would get the same thing if you tried to use this form. So what this form does is it defines h as being this distance between the 2 points. Well, what's the difference between 3 and 7? It's still 4 units. So the bottom would still be 4. Notice that here, 7 minus 3 is 4. And then on the top, if you think of x1 as still being 3, that initial point, 3 plus 4 would be 7, so this is still f of 7 minus f of 3. It's really the same format. There's going to be a very good reason why we use this one, and we'll see that here, I don't know, probably in just a couple minutes. All right, so we have our average rate of change, it's 160. Super important here. If we had any units, okay, I didn't give us units on this one. Think, you're driving a car, miles per hour, that kind of thing. That's what a rate of change is. It's a comparison of units, right? If you're driving 70 miles per hour, that is a rate of change in where you are at, right? You're changing where you are at 70 miles per hour. And so if we have units for x and y, or for x and f of x, those are going to give us a description of what that rate of change actually is. Okay, so for instance, if you took a ball and you dropped it, the rate of change might be measured in feet per second or meters per second. And so those, right, because feet would be that y distance that the ball drops, and seconds would be, presumably the units of measurement that we would use to measure that. And so we get the units, and it gives us a really nice description of what this rate of change actually is talking about. So in this case, we didn't have any units, but sometimes we will. All right, so let's take this just a little bit further. We have some more fun to be had. Let me get a new board. Okay, so now we have a really pretty important concept to try and talk our way through. So you'll notice I don't have a lot on this board right now. We'll get into a real example here in just a minute. But I want to talk about a tangent line, okay, and what that's going to mean. And so I'm going to set that up a little bit. I'm hiding a little bit behind my back. Maybe you got a glimpse at it there for a second. But I am hiding a little bit behind my back for the big reveal. So here's what we have. I want to talk about the slope of a line at a point P. And you're like, wait a second. Slope measures, rise over run between 2 points, right? I mean, that's what we have always learned. I know, isn't this going to be fun? Anyway, sorry, I'm a little giddy. I like calculus. This is good stuff. So what we're going to do is we're going to consider 2 points. Okay, I just have a generic graph here, and we're going to consider 2 points on the graph. And normally we could find the slope, no problem. So I'm using x1 and x1 plus h. Here's that notation again that we saw on the last board with the average rate of change. And so remember, h is just something that's added on to this first x value, which gets us another x value. So the idea is pretty simple. We're going to drag these 2 points together. That's why I have this arrow here, kind of showing this right-hand point moving toward that first point. In other words, what we're going to do is we're going to force h to get very, very small. How small? Almost, but not quite 0. How small is that? As small as we want it to be. That's really kind of the case. That's really what we're looking at here. It's as small as we want it to be. And the idea is we're going to try and figure out where this slope is going as h gets smaller. So we could do this with a function. We could have an x value, and we could have a function value attached to it. We could have an x plus h value, and then we could take that h and make it smaller and smaller and smaller and see what happens to that slope, to that average rate of change. And that's something that you're going to do in your homework here, I'm pretty sure. So anyway, let's take a look at the rest of this board. This kind of line where you have 2 points, that connects 2 points on a curve, is called a secant line. A tangent line is the limit of the secant lines. And limits are what this first chapter is all about. You're going to have so much fun with them. And we're just going to kind of get started on this conceptually just a little bit right now. Like I said, the idea is what happens to this slope as we take that limit, as we drag those points together. Okay, obviously, we can't find an average rate of change with only 1 point, but we can make the distance between those points smaller and smaller and smaller and smaller. And that's really our first basic idea of what it is to take a limit. Let's do an example. All right, so here's the problem I want to do. Find the slope of the parabola, y equals x squared, at P416. P416, in case you're not familiar with that, that just means the point 416. It's probably worth checking, but yes, 416 is actually on the parabola, right? If you plug in 4 for x, 4 squared is 16. So this is just 1 point on the parabola, and we're going to try and find the slope at 1 point. So what we can't really do here is use the y2 minus y1 over x2 minus x1 definition of a rate of change. we're going to have to use f of x1 plus h minus f of x1 all over h. That's going to be the form we're going to use, because again, what we're going to do is we're going to kind of have some fun with this, and we're going to make h get really small, and we're going to see what happens. You can see what happens because I had to write it here, but the slope will end up being 8. All right, let's get to the work. So I need x1 here is the 4. That's the point we're looking at. So I have f of 4 plus h minus f of 4 all over h. Now, I kind of recommend, and I didn't have room to do this here, so I did it all in the middle of the nastiness. Honestly, if I had more space on this board, what I would have done is I would have divided my board, and I would have taken this 4 plus h squared off to the side, and I would have expanded it, and I would have taken the 4 squared off to the side, but it's pretty easy. Be really careful of the minus sign. Don't lose those minus signs. So if you do expand the 4 plus h squared, you get 16 plus 8h plus h squared. We still have then we have the minus 16 from the 4 squared. The 16s are nice enough to get rid of each other. And here's the thing, that's probably going to happen on most of these. So the 16s go away. We get 8h plus h squared over h. And now, here's what we want to have happen. I mean, you can see that I have a couple more steps here. We want to take h and drive it very, very close to 0. We want it to get arbitrarily close. But we can't divide by 0, so we can't just plug it in. So we have to do a little bit more work to clean this fraction up so that then we can just basically call h 0. So hopefully you notice that both terms on top have an h in them, so I factored out an h. That's a very common little trick that you'll see with these. And when you do that, the h is canceled. The one on the top that we factored out with the one that was on the bottom. And so we're just left with 8 plus h. And so what happens is this. If you want to think about this as a series of points that are, again, coming and getting closer and closer and closer to our original point, what happens is we could say, okay, the slope at, 4.1 would be, right, 8, if we want, or between, let me try that again. The slope between our point and the point where x is 4.1 would be 8.1, because h there would be that 0.1, right? That little difference to where we started. And so basically we're driving down to 0. And so once we get here, then we just do it. We just say, all right, let's let h be 0. And if h is 0, our slope is just the 8. So that's very fun. It's very exciting. This is certainly something we're going to come back to. Oh boy, will we come back to this. And you guys are going to probably not care for it very much, because there's some messy stuff coming. All right, I have one more last tiny little bit. I want to expand on this problem just a little bit more, so hang in there. All right, so the first half of this board is same as it was just a minute ago. All I added in is I want to finish up this problem, in this case, by finding the equation of this tangent line. So again, we have a point. We found the slope of this tangent line, right? We found that that was 8. And we want to find the equation of the tangent line at that same point. So I'm just going to go back to some introductory algebra material. This is the equation of, this is the point slope form of the equation of a line, right? Y minus a y coordinate is equal to the slope times x minus the x coordinate. And I just fill all those in. My y coordinate is 16, so I have y minus 16. My slope was 8, and my x coordinate was 4. Make sure you put them in the right places, right? X and y here are your variables. And if you could leave it there, that's fine with me. Or if you want, you can put in slope-intercept form. And if you do, you're going to get y equals 8x minus 16. So thanks for watching the video. Hopefully that was as fun for you guys as it was for me. And have a great day.